some nuclei cannot gain stability through a single emission. So in order for some radioactive nuclei to become stable, they need to go through successive emissions. They'll go through an alpha, a beta, go through another alpha, maybe a few more betas. This is called a radioactive series. So you'll notice here with these blue arrows, these are all alpha emissions. And then the red arrows here, these are all beta. So uranium-238 will go through an alpha, beta, beta, alpha, 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 beta, beta, alpha, beta, beta, alpha to become stable at Pb206. Now, the rates of each of these decays are different. Uranium U-238 takes about 4.5 times 10 to the 9th years to decay, half-life, where plutonium 214 takes 1.5 times 10 to the negative 4th seconds. So the rate, half-life rate of each of these decays is much different. So depending on the stability and the half-life, it could take a very long time for it to decay one step, or it could be very quick. Another method of prediction is magic numbers. Nuclei with 2, 8, 20, 28, 50, or 82 protons, or 2, 8, 20, 28, 50, 82, or 126 neutrons are generally more stable. This is just a pattern that they've noticed. Also, it said that nuclei with even numbers of both protons and neutrons are generally more stable. So just a few things to keep in mind when we're looking at the stability and trying to predict whether a radionuclei will go through a decay and what type of decay it needs to go through. Nuclear transmutations. This is a change of a nucleus by bombarding it with a neutron or another nucleus. Particle accelerators or atom smashers are used to do this. So an example would be nitrogen-14 is bombarded with an alpha particle. So we have nitrogen-14, which is just a normal nitrogen atom, but these particle accelerators take these atoms and they smash them together with an alpha particle or some other type of nucleus. And what ends up happening is that they will have new things created. Sometimes it will be a single atom, or other times it will be 2 or more new atoms that are smashed together. So if we take a look, this equation here, this nitrogen-14 bombarded with an alpha particle, is actually found on page 901 of your book, at the very bottom. When this happens, they found that oxygen-17, an isotope of oxygen, will be produced, and so will a hydrogen atom. So we've created oxygen-17 and hydrogen from taking a nitrogen atom and bombarding it with an alpha particle. A lot of times this is how they are developing, or they are researching or discovering these new elements. The elements that are still yet to be named is through these particle accelerators. Now, a sample problem would be from 21.27 from the homework section of your book. And it says, complete and balance the following nuclear equations by supplying the missing particles. So we'll do one example of it. So here we have an A of this problem. We have 252, 98 CF. And we are going to bombard that with 10, 5B, so boron 10. And it tells us we will get 310N, and it wants to know what else is formed. Well, just like in any other reaction, this 3 here indicates that we have 3 neutrons. So here, this will actually mean 3N. So over here we have 262, and then 98 plus 5 is 103. So on this side, we need to have the same thing. So what plus 3 gives us 262? We got 259, and then 103. So we look at our periodic table, and we have 103 as lawrencium, which is Lr. So this is our answer, 259, 103, Lr. And you could go through and do B, C, D, and E as practice to help you through. Our rates of decay, we did this during kinetics, so this is not a review, or this is not new, this is a review. Kinetics rate of decay, we have our natural log of NT over NO, which equals the negative KT. T is your time interval of decay. N sub 0 is our initial number of nuclei. N sub T is the number remaining after a time interval, and K is our decay constant. Please note that our N sub T divided by N sub O can be a ratio of the mass or the ratio of activities. And we're not really going to get into activities, so we're going to be looking more at masses. Our half-life is the time for half of the amount of a radioactive, unstable proton-neutron ratio material to decay. So how long does it take for half of the substance to decay, and then how long does it take for the half of that to decay, and so forth, so on. So here's our equation. This should not be a surprise. This is from chapter 14. We did this with our rates. All right, if we start with 1 gram of strontium 90, 0.953 grams will remain after 2 years. What is the decay constant? What is the half-life? And how much will be left after 5 years? We are going to use ln of T. We are going to use ln of n sub T over n sub 0 equals minus KT. So in the first part, A, we are going to solve for K, and we get negative 1 over T ln NT n sub 0, which ends up being minus 1 over 2.00 ln 0.953 over 1.000. And we get 0.0241 years raised to negative 1 as our K. Once we know K, we can solve B by using our half-life equals 0.693 K, and that ends up 0.693 divided by 0.0241 year, which ends up being 28.8 years is our half-life. Then finally, with C, we can use our original equation up here and plug in our K and our T, which is 5 years. So we'll get ln of NT sub n, or divided by n sub 0, and we will get minus 0.0241 times 5.00 years. And this is going to equal negative 0.120. If we solve for NT in sub 0 here, we need to take the E of both sides, and that cancels out the natural log. Then NT will equal this answer, which ends up being 0.887. So we can take 0.887 times the n sub 0, which was our original value of 1 gram, and we get after 5 years we'll have 0.887 grams of strontium-90 left. So a very good example of how to use the equation to solve for K, half-life, and then using the K and a new value to find the amount remaining after a certain period of time. Okay, the energy changes in nuclear reactions will relate to a change in mass. So the mass lost during radioactive decay is released as energy. It's important that you keep in mind that the mass in the change in E equals the change of N, M times C squared, is in kilograms. The kilograms helps us get to joules as our unit. So the mass defect here, or the change in mass right here, is the difference between a nucleus and its nucleons. The nuclear bonding energy must be added to a nucleus to break it into its parts, its neutrons and its protons. When energy is added, the neutrons and protons separate and they will gain mass. So an example of this is how much energy is lost or gained when a mole of cobalt-60 undergoes beta decay. Cobalt-60 is 5.9338 AMU and Ni-60 is 59.9308 AMU. Start by writing the equation. So we have 60 cobalt, which is number 27, and it's going to go through a beta, which is a electron, and you're going to get 6028 Ni. Now, before you go through and actually begin the change in energy, you need to figure out the change in mass, which is of the nucleus only. So you have to take the mass of the nucleus by removing the mass of the electron. So for cobalt, cobalt's mass is 59.9338, and we need to subtract the mass, because even though we say electrons don't have a mass, they do have a mass, and when we're talking about nuclear, we need to take that into consideration. So we have 27 electrons, and each of them weighs 5.4858 times 10 to the negative fourth. So if you go through and do this calculation, you get 59.919 is the mass of cobalt. You're going to do the same thing with nickel, which is 59.9308, and this will end up being 28 electrons because nickel is atomic number 28 by the same amount. We get 59.915. Now the change in mass will equal the mass of the products minus mass of reactants. So our products will be electron plus nickel minus our cobalt. Because remember, we have one electron, one beta particle. So this will be 5.4858 times 10 to the negative fourth plus 59.915 minus 59.919. And that gives us a change in mass equaling negative 0.00345. Now that we have the change in mass, we can find the change in energy by plugging that in. Remember, 2.99 times 10 to the 8th meters per second. That is our speed of light. We square that, and we're going to multiply it by negative 0.00345. But remember, our grams, this is in grams, we need kilograms. So 1 kilogram over 1,000 grams if we do the math of this, this ends up being negative 3.086 times 10 to the 11th kilograms times mass squared divided by second squared, which ends up equaling a joule. So we've got negative 3.08 times 10 to the 11th joules. What's important to remember is we need to account for the electrons as a product if it's a beta decay and include that in our change in mass. Last thing I just want to discuss real quick is the fission infusion. Now, fission is a process where they take an atom and they split it into new atoms by bombardment. So we'll have a loss of mass. This loss of mass will also result in a release of energy. So you'll notice if you take uranium-235, bombard it with a neutron, you'll get 2 new products and energy, along with a few neutrons, which are now then available to hit other uranium atoms to create a whole chain reaction. Then finally, fusion. Fusion is actually the combination of 2 nuclei, so some mass is lost, which results in a release of energy. So we're going to combine 2 nuclei, mass is lost, energy must be released. So we take hydrogen 3 and hydrogen 2, try to fuse them together to form helium, and in doing that we release a neutron and we release energy. So that's a real quick overview of fission and fusion. You should just know what's occurring with both. And that covers all of our nuclear energy chapter and our nuclear chem. So hopefully, if you need to, review, read the book, make an outline, and you should be ready for the test.